Okay, I want you to join me for a second. Just step into two completely different worlds.
Okay.
Picture child A. They're maybe 3 years old,
Mm-hmm.
and their challenges are, well, immediate. They're right there in front of you.
You can see them.
You can absolutely see them. Struggles with eye contact, largely nonverbal. They showed clear developmental delays pretty much from infancy.
Mm-hmm.
Didn't walk when other kids did. Didn't have simple words at 2.
Yeah.
So for the parents, I mean, the red flags were just huge.
Huh?
And they got a diagnosis around age 3.
Right. Very early.
Now, hold that picture, and let's switch to child B.
Okay.
Child B is 14. Highly articulate, maybe even top of their math class.
So, on the surface, totally functional.
Totally. They're in the system, but they are just burning out.
Yeah.
Every single day.
I can imagine.
Debilitating anxiety, walking into the school cafeteria. Every conversation feels like some kind of complicated play they have to perform.
That's called masking. It's exhausting.
Right. And they crash every night. They just got their diagnosis at 14. After a whole decade of being told they were just, shy or moody.
Or that it was just anxiety.
Exactly. So here's the thing. Both of these kids, they have the exact same clinical label, Autism Spectrum Disorder.
But their realities are worlds apart.
Worlds apart. The experience, the needs, and the thing we're digging into today. The timing of that diagnosis.
Right.
Why?
Yeah.
Is that difference in the age of diagnosis, the AOD, is that just the system failing? Did one kid get lucky with doctors and the other didn't?
Or is it something else?
Right. Or is that gap telling us something deeper, something biological? Is the timing itself written into their DNA?
That paradox is, that's everything. That's the frontier of where the research is right now.
Really?
What you just laid out, that huge difference between child A and child B, it confirms that the ASD label, it's an umbrella.
A huge one.
A huge one. And it's covering what are probably several completely distinct biological conditions.
But we suspected this for a while.
For decades. But it was just a suspicion.
Yeah.
Now, because of these massive, and I mean massive, genomic studies, we have the evidence.
Okay.
And so that's our mission for this deep dive. We're going to unpack this incredible finding that ASD isn't one disorder. It's a collection of genetically distinct subtypes.
And the genetics determine the timing.
That's the punchline right up front. The underlying genetics dictate not just what symptoms you see, but when they become visible enough to trigger a diagnosis.
So the age of diagnosis is less about luck.
And far more about molecular timing.
Okay, so let's set the stage here. Let's talk about the villain of this story, which is really the current state of diagnosis.
The spectrum.
Yeah, we call it a spectrum. And that word makes you think of this like neat and tidy line from one end to the other.
Like a color wheel.
Exactly.
Yeah.
But the reality, what the sources are telling us is that the clinical picture is so wildly diverse.
From nonverbal with global delays to, like you said, a kid acing math but socially exhausted.
Right. So we should really be talking about the autisms, plural.
That is such a crucial point. That word spectrum, it's actually held us back, I think.
How so?
Well, because it makes you think things fade smoothly from one to the next. But the biology, it's more like a warehouse.
Right.
A warehouse full of completely different machines. But they all kind of produce a final product that sounds the same.
And the final product is the diagnosis.
The diagnosis. And because that diagnosis is based only on watching behavior, we treat the product as one thing, even if the engines inside are totally different.
And when you look at the cost of this spectrum mess, the stakes are just, they're colossal.
Oh, yeah.
This isn't just about stress on a family. This is a national economic issue.
It absolutely is.
The sources point to this projection that is just staggering. The direct and indirect costs. So we're talking special ed, healthcare, lost wages.
The whole thing.
It's projected to hit close to $500 billion.
Billion with a B.
By 2025. In the U.S. alone.
Yeah.
A $500 billion problem.
And that number is a direct result of the problem we're talking about, this heterogeneity.
Explain that link.
Well, if we had one clear biological target, one single type of autism, we could develop targeted effective treatments.
And the cost would go way down.
They'd plummet. But because we're basically throwing one generalized set of behavioral therapies at hundreds of different conditions.
It's super inefficient.
Highly inefficient. And so the financial cost and the human cost, it just keeps spiraling.
So what are researchers up against? What makes it so hard to untangle?
It comes down to the genetics. It's this concept scientists call extreme locus heterogeneity.
Okay, that sounds like a $50 term. Break that down for us. Locus heterogeneity.
It really is, yeah. But it's just a fancy way of saying genetic anarchy.
Huh. Okay. I like that better.
A locus is just a spot on a chromosome, location. And heterogeneity just means diversity or variety.
So a huge variety of locations.
An extreme variety. It means the same condition, ASD, can be caused by errors at hundreds, maybe thousands of different spots scattered all across your DNA.
So you're not looking for one broken part.
You're looking for one broken part out of 500 possible parts. And they don't even all have the same impact.
Which gets us back to our two kids.
It gets us right back. It leads to those two extremes.
Okay, so walk us through those extremes again, but maybe with an analogy so we can really picture it.
Absolutely. So on one end, you have the really high impact, rare variants. Often it's what's called a de novo mutation.
Meaning it's brand new, not from the parents.
Exactly. And this one single mutation can be powerful enough all by itself to cause ASD.
This is the game-breaking relic we talked about. You find this one item, and it just fundamentally changes everything about your character immediately.
That's a perfect analogy. It's a huge instant change in the blueprint. It basically guarantees a certain outcome, and that usually means severe early symptoms.
Okay, that's one extreme. What's the other?
The other end is what accounts for most cases. It's the accumulation of common variants, polygenic risk.
Poly meaning many.
Many genes. It's the buildup of maybe over 1,000 low-risk genetic markers.
So these are tiny genetic quirks we all have, but for some people, they just get a bad roll of the dice and collect too many of them.
Exactly. The total number crosses a certain threshold.
So how do we picture that?
Okay, think of building a big, complex wall. The single de novo mutation, the rare one. That's like finding a giant crack in the foundation.
You'd see it right away. The whole wall would be leaning.
Immediately. It's obvious. Now, the polygenic risk, that's like having 1,000 tiny microscopic flaws in every single brick.
Ah, okay. So no one brick is a problem.
No. Individually, they're invisible. But when you stack up 1,000 of those slightly weak bricks, the whole structure eventually becomes unstable.
But much, much later.
And that's the key. Much later, it starts to crack under pressure.
And the big problem is that our whole diagnostic system is based on just seeing the cracks.
Yes. On observing the aberrant behavior, it's not about knowing what's wrong with the bricks or the foundation.
We don't have a way to look at the blueprint.
We don't have that objective biomarker. No simple blood test, no brain scan, so it all comes down to subjective things.
Parent reports, teacher observations.
The clinician's own experience. And that system is completely dependent on how loud the symptoms are.
So if the cracks are subtle?
Or if the person is really good at hiding them, at masking, or if the behaviors only really show up years later.
The system misses them.
It completely misses them, and that is what fuels the delay for child B.
So with all that in mind,
Yeah.
what was the thing that made researchers think, wait a minute, maybe the age of diagnosis is biological? That seems like a big leap.
It was a huge leap, and you're right to ask that. The clue is in the patterns.
What kind of patterns?
In the co-occurrence of traits. For years they just used a checklist. But when they looked at these giant data sets, they saw clusters.
Clusters?
Yeah, like they'd see that high anxiety plus subtle social problems. That cluster seemed to go with certain genetic factors, and it consistently showed up later.
Later than what?
Later than the clusters that included intellectual disability, the AOD, the age of diagnosis. It wasn't random. It seemed to be following these unwritten genetic rules.
And that's when they decided to investigate it directly.
That's when it became a trait worth studying in its own right.
So you've got this gigantic, messy, unclassifiable spectrum, the autisms, and a bunch of researchers realize they have to stop just looking at the surface behavior.
Right. They needed a map of the biology underneath.
It sounds like a quest. Like, how do you even start to categorize that kind of chaos?
It took a truly heroic effort. And it meant flipping how science usually works on its head.
How so?
They needed scale. Unbelievable scale. And that's where these huge projects like SPARK came in.
SPARK.
Simon's Powering Autism Research for Knowledge. It's a massive collection of data, clinical profiles, genetics, everything from over 5,000 autistic people and their families.
Wow.
And that scale is what lets you connect the full clinical picture with the full genomic picture.
And you said they had to change their method?
Yeah, the key was moving away from what we call trait-centered research.
Right, the banana analogy. Don't just look at one thing in the grocery cart.
Exactly. A traditional study might look at, say, 500 people who all have high rates of repetitive behaviors.
Okay.
But they'd ignore everything else. So you don't know if that behavior is from a severe developmental delay or if it's a coping mechanism for anxiety that showed up later.
You're totally missing the context, the whole person.
You're missing the whole person. So they realized they needed a person-centered approach.
And how do you do that with so much data?
You need some serious computational power. They use something called general finite mixture modeling.
Okay, another big term.
It is, but think of it like an unsupervised clustering algorithm. It's a really smart computer program.
What do you mean by unsupervised?
It means you don't tell the computer what to look for.
Ah,
In a normal statistical test, you might say, hey, does low IQ predict an early diagnosis? You're testing a hypothesis.
right.
With this method, you just dump all the data in. IQ scores, anxiety levels, motor skills, genetic risk scores, AOD, everything from all 5,000 people.
You throw the entire grocery store on the floor.
You throw every single grocery cart onto a giant warehouse floor and you tell a supercomputer, find the patterns, tell me if there are natural hidden groups in here.
So you let the data define the subtypes.
You let the data define the subtypes instead of forcing your own clinical definitions onto the data. It's a game changer.
And the age of diagnosis.
Yeah,
The AOD, that was one of the things you throw onto the floor.
it was. And that was the fundamental insight. They confirmed it's not just a social or demographic thing. It's a genetically influenced quantitative trait.
A trait you can measure that's influenced by genes.
Exactly. They used something called a genome-wide association study, or GWS.
Right.
It scans the whole genome for those little common variants, the SNPs, that are linked to a specific trait.
And they found a link to AOD.
They found that these common genetic variants accounted for about 11% of the variants in the age at diagnosis.
11%. How big a deal is that? I mean, when you think about things like access to doctors, parental income.
It's a massive deal because all those social and demographic factors you just mentioned, they usually account for less than 15% of the variants combined.
Wait, really? So the genetic pull is almost as strong as all of those real-world factors put together.
Nearly as powerful, which tells you this isn't just a byproduct of the system. AOD is an active biological process.
And that's driven by the polygenic risk score, the PRS.
Correct. That cumulative risk from all those tiny, weak variants.
We really need to nail down the difference between that and the single big mutation.
We have to. The single high-impact de novo mutation, that's a lightning strike.
Boom. Instant. Defines everything. That's child A.
That is child A. But the polygenic risk score, the PRS, that's more like the climate.
The climate.
Yeah. It's the slow, steady result of hundreds of little genetic factors subtly affecting things like how efficient your brain pathways are or how prone you are to anxiety.
It's the experience points from the video game analogy.
It's tracking the XP. It's the slow build that only really becomes a problem when the game difficulty gets turned up.
Like in adolescence.
Like in adolescence, when the social demands finally push the system past its breaking point, and that's when you get the late diagnosis.
So one is an immediate structural problem. The other is a slow, cumulative functional problem.
That distinction is the key. That's the fork in the road. That's the two biological highways they discovered.
Okay, this is it, the big reveal. They run this massive analysis. They let the computer find the patterns in the chaos. What did it find?
It found that the spectrum isn't a spectrum. It resolved into 4 distinct biologically real clusters.
4. Okay, tell us about the 2 that really explain the gap between child A and child B.
The analysis just cleanly split the participants into 2 groups with totally different stories.
Okay, group 1.
Group 1, about 19% of the participants they called mixed ASD with developmental delay. This group is the perfect picture of the early onset pathway.
So this is child A's.
This is child A to a T. Clinically, they had global delays, late to walk, late to talk, and crucially, very high rates of co-occurring intellectual disability.
So why does their biology force that diagnosis to happen so early?
It's all about the timing of their genes, the specific genes affected in this subtype. They were mostly active prenatally,
Before birth.
way before birth. During the foundational construction of the brain, these genes messed with fundamental stuff, like how neurons travel to the right place.
So if the brain is a highway being built in the womb.
This genetic problem was like having faulty concrete and bad scaffolding from the very beginning.
So the structure itself is compromised.
The structure is compromised, and the result is immediate, obvious delays across the board: motor, language, cognition. These are symptoms you just can't ignore. They're red flags that push that diagnosis way, way earlier.
Okay. Structural problems from prenatal genetic activity. Got it.
Now, what about the other big group? This was the largest group at 37%. They called them the social and behavioral challenges subtype. This is your late onset pathway. This is child B.
Okay, so what's their story?
Clinically, their defining feature was hitting all those early milestones on time.
They walked and talked on schedule.
Exactly. But they struggle massively with executive function and have really high rates of psychiatric issues, ADHD, anxiety, depression.
So their foundation was okay. When did their genes kick in?
Theirs were mostly active postnatally, after birth.
Wow. Okay, that's a huge difference.
It's everything. The genes in this subtype affect the maturing brain. Things like refining the connections between neurons and developing the circuitry for complex social thinking.
So it's not a structural failure, it's more like an efficiency problem.
A functional efficiency problem. And it only really shows up when the world gets complicated, like navigating middle school.
So because they passed all the early tests.
The diagnosis was delayed, and this group had the latest average age of diagnosis in the whole study.
And you said there are two other groups, just quickly?
Yeah, they sort of filled in the gaps. Moderate challenges was a milder version of that second group, and broadly affected was a small group that was severe across every single domain, like a combination of both problems.
Okay, but let's stick with that late onset group, the social and behavioral challenges group.
Yeah.
You said their genetic profile looks different. How different?
I mean, profoundly different. When they looked at the polygenic risk scores for this later diagnosed group, they found those scores were moderately to highly correlated with the PRS for things like ADHD, major depressive disorder, and get this, PTSD.
Wait, stop. Stop right there. So you're telling me that the genetic signature of the late diagnosed autistic group overlaps more with psychiatric conditions like ADHD and PTSD than it does with the early diagnosed autistic group.
That's what the data shows. In fact, they found little to no overlap in the molecular pathways that were affected between the two groups.
That's mind-blowing. They're biologically different conditions.
They really seem to be. The genes for the early group are about building the brain itself. The genes for the late group seem to be about regulating neurotransmitters, dopamine, the stress response.
All the things that control anxiety and attention.
Exactly. And that genetic overlap explains the clinical picture you see in child B.
The anxiety, the attention issues.
It all makes sense. They're struggling with executive function, which looks like ADHD, and they're struggling with this chronic internal stress from a lifetime of masking, which looks like anxiety and depression.
So the anxiety isn't just something that happens to them because they have autism.
It might be a core genetically linked feature of their type of autism.
Wow. It's not a comorbidity, it's part of the package.
That's the paradigm shift this research is pointing to.
Okay, so the genetics can act like an accelerator, pushing for an early diagnosis. Let's really dig into what those accelerators are in the real world. What's the biggest one?
By far, the most powerful accelerator is the presence of intellectual disability, or ID.
Right, which was a defining feature of that first group.
It is. ID and ASD share a lot of the same molecular machinery, and its presence just creates this unambiguous clinical picture. A doctor sees it, and they know something is seriously wrong.
And you mentioned there was a specific time difference, right? Something like 6 months. Why is 6 months such a big deal for a toddler?
It's because of the critical window of brain development.
Synaptic plasticity.
That's it. Between the ages of 2 and 4, a child's brain is just exploding with new connections. It's when the foundations for language and social skills are being laid down at incredible speed.
So every month counts.
Every single month, you delay getting that kid into intensive early therapy. That's a lost opportunity. That's 6 months, going from a diagnosis at 49 months down to 43 months for those with ID.
It means you start the intervention before those critical windows start to close.
Exactly. This severity of the ID forces the system to move faster, which is actually a huge benefit.
So severity drives speed, and speed maximizes the impact of the therapy. That's huge.
And that speed is pushed even faster when you look at syndromic conditions.
Where you know the specific gene mutation from day one.
Right. A classic example is tuberous sclerosis complex, TSC. It's caused by mutations in one of 2 genes, and those mutations often guarantee a tough neurodevelopmental outcome, including ASD.
So if you know a baby has the TSC mutation, how early can you spot the signs of autism?
This is where it gets really amazing. Because these infants are known to be high risk, they're watched like a hawk. And researchers have shown they can spot deficits in social communication.
Like what?
Things like reduced attention to faces or not following someone's gaze.
Hmm.
They can see these things as early as 9 months of age.
9 months.
9 months. Now, compare that to the average diagnosis age of 47 months in the general population.
You're bypassing the delay by more than 3 years.
You're proving that the problem is already there very early on. The only thing delaying the diagnosis for most people is that we don't have that flashing red light from the genetic tests.
The single huge genetic error is the ultimate accelerator. Okay, now let's talk about the brakes, the decelerators. The late diagnosed groups were delayed because they hit their milestones. But there's another huge factor that slows things down: gender.
Gender bias, it's a massive issue.
Females are diagnosed so much later than males, something like a 4-to-1 ratio. How does this new genetic research explain that?
This is one of the most important connections this work has made. We've heard about this female protective effect for years.
Right.
What this research suggests is that the female biological system might require a much heavier genetic hit.
A bigger dose of the bad genes.
A bigger dose or more powerful rare mutations to show that classic severe early onset phenotype of child A.
So if a boy and a girl have the exact same rare mutation, the girl might not show it as severely.
That seems to be the case. Her system has some kind of buffer, which means that when a girl does present with that classic early onset picture, her genetic profile is often extremely severe.
So the data actually shows this.
Yeah, the sources show the genetic correlation with that early diagnosed factor is significantly stronger in males.
And on the flip side,
Females with a lower, more polygenic risk, the cumulative XP points model, are much more likely to have that subtler presentation.
their challenges show up later.
They show up later and they're focused on internal things, like anxiety and social camouflage.
That sounds exactly like the late onset subtype, the social and behavioral challenges group.
It maps onto it perfectly. Females are more likely to fit that profile. They mask their way through childhood, and then they hit a crisis point in their teens when the social world gets too complicated and the anxiety just explodes.
And the system, which is built to find child A.
The system, which is designed to catch the early, severe, mostly male phenotype, misses them completely.
So it's not just that doctors are biased. The biological presentation in females is fundamentally different, and our tools aren't built for it.
That's the core realization. The female phenotype often is the late-onset genetic subtype, and it's inherently designed to be missed by our current model. So if we bring this whole journey together, what this investigation really confirms is that the age of diagnosis isn't random. It's a powerful reflection of the biology underneath, specifically when the affected genes are doing their work.
Prenatal versus postnatal.
Exactly.
Yeah.
Early prenatal genetic issues cause structural problems, global delays, and a fast diagnosis. Later, postnatal polygenic issues affect functional systems, stress, attention, and that leads to a late diagnosis with that heavy psychiatric overlap.
Which means the one-size-fits-all approach just has to end.
It has to.
If we can now genetically slice autism into these cleaner subgroups, what's the next step? How do we get this into the clinic?
The most powerful tool we have right now is genetic sequencing, specifically whole exome sequencing, or WES.
Okay.
The clinical yield, the chance of finding an answer from genetic testing in neurodevelopmental disorders, is the highest of any medical test in the field. For general ASD, you'll find a clear genetic cause in about 23.5% of cases.
Okay, almost a quarter. That's pretty good.
It is, but watch what happens when you focus on that first subtype we talked about.
The early onset group with ID.
In cases of ASD with co-occurring intellectual disability, your child, a type, the yield from genetic testing jumps to an incredible 52 to 53%.
Wait, over half?
Over half of the most severe cases have a definitive genetic answer waiting for them.
That feels like a slam dunk case for making WES the standard first test, especially for kids with early delays.
It absolutely does. It changes the diagnosis from just a behavioral label to a confirmed biological cause. And knowing the gene is crucial for care.
How so?
Well, if you identify a condition like TSC, the doctor knows exactly what to watch for, not just behavior, but things like epilepsy. So they can start proactive screening, like regular EEGs.
And what about the late onset group? What does this do for them?
It enables the targeted screening they desperately need.
Okay.
If someone's genetic profile points strongly toward that late onset pathway, with the high correlations to ADHD and anxiety, then their clinical care shouldn't just be about social skills. It should be about proactively monitoring and treating the mental health issues that are part of their biological signature.
So for the Child B subtype, we're talking about maybe specialized ADHD medication or therapy for depression, not just practicing eye contact.
Exactly. Because their primary struggle is different. You stop treating just the symptom, the social withdrawal, and you start treating the underlying cause, which might be the crippling anxiety or the executive dysfunction.
That feels like the future, where molecular psychiatry and neurodevelopment finally come together.
That's the promise.
Which brings us to our final thought, a provocative question for you to take with you.
Lay it on us.
The research seems clear. The age of diagnosis is biologically driven. So if we accept that late-diagnosed autism has this unique genetic footprint, one that overlaps heavily with conditions like ADHD, PTSD, and depression, should we still be treating it with a diagnostic model, a treatment model that was designed primarily for toddlers with severe developmental delays?
It's a powerful question.
The science has split the spectrum. And the challenge now is to make sure the clinic, the schools, and the support systems all catch up so that every person gets the specific genetically informed support they need right when their biology says they need it most.